Welcome everybody, my name is Matthias Luft. This is Felix Wilhelm. We both work for ENW and we got constantly teased about how we have to present like the hypervisor breakout at Troopers. Let's say we will present why this is not easily possible using this vulnerability, just as a short disclaimer at the beginning. However, there will be a practical demonstration of an exploit against Hyper-V. Okay, the title of our presentation is Compromise as a Service with a slight emphasis on Azure. As the whole research on the topic started with a research topic on Azure security. And we will have three main parts in our presentation. First, we will cover Azure and Hyper-V and how they are related to each other. Tell you a little bit about the research project, what it did cover in that project and what not. Then we will have a look at clouds and hypervisors in general, provide a little bit of a taxonomy on attack vectors. If you want to get engaged in hypervisor or cloud security research, what areas you should particularly focus on. And then the third and main part will be Hyper-V, its architecture, potential attack vectors, and of course our research results that we gathered in the course of that research project. Of course, feel free to ask questions at any time. It was also really nice that Rodrigo also covered a lot of the really low-level topics that we were also looking into or that we had to deal with. So at least we can make some references to his talk where it's appropriate. All right, we'll start with a short introduction to the research project and the Microsoft Azure environment. We were engaged in a government research project focused on the overall security posture of the Azure cloud environment. We did this together with ThinkTecture. I promised to include them in the talk, so I don't think Christian or Dominic could make it here, but if you watch the recordings, hi guys. And it had a scope on the overall security posture of Azure. So not exclusively focused on hypervisor security, but also on network security in the cloud environment, then of course virtual machine isolation, and also management interfaces, the security of those interfaces. The ThinkTecture guys also had a look at all the identity services offered by Azure, but this is not part of our research. When you're following somewhat a structured approach of security research, we of course have to first think about the security objectives for a particular asset. And for a cloud environment, of course, this is availability. Not only for the cloud service provider, but also as a customer, you have to think about the availability of your services. Cloud downtimes of particular services have been a regular occurrence in the past. So you need to think about that, especially after seeing this talk, because there will be some availability impact available. Then, of course, one of the major security objectives in cloud environments, or at least the main one everybody is talking about, is isolation. If you want to put that in a more general way, safeguarding the confidentiality and integrity of clients against each other. So again, the classical three old security objectives, CIA, that you have. The only thing that is maybe relevant, a lot of people tend to confuse security of the hosted guest systems and how to secure those with the security of the overall cloud infrastructure. This is something I like to strictly handle differently. Some people always mix it up, but we will focus on the infrastructure of the cloud environment exclusively here. And looking at cloud environments, we developed four main areas of attack vectors that can lead to isolation failures in cloud environments that we like to use when we're performing cloud security assessments or consulting or workshops on cloud security. The first one, of course, is a runtime breakout, or what we call a runtime breakout. This is like the most infamous attack always discussed in cloud environments. What if I can execute some code in a guest system that results in code execution in the host system? The most interesting part, of course, and this is also what we will mainly cover in our presentation. That's why I won't tell you too much here. Then, of course, storage breakout or isolation failures are also very important. It's nice if your virtual machines at runtime are completely isolated, but if some access controls in the storage backends are not completely implemented, or you can do some kind of basic directory traversal attack, it also results in a lack of isolation on your hosted data. Then, of course, you want to have an isolated network, which means that other clients should not be able to eavesdrop on your traffic, at least in the network segment that is hosted at the cloud service provider. Then, from our point of view, a very, very important part are management interfaces. All cloud management interfaces are typically web applications or web services, and I think I don't need to tell you too much about the security of web applications in the world out there. So this is a very important aspect, also not part of this presentation. So, having those attack vectors in mind, I will give you a short introduction to the Azure environment, also in order to show you why all those attack vectors matter and why hypervisor security matters in particular. So an Azure data center is always consisting of a so-called fabric. The fabric has some big data center routers in the middle. Then we have several clusters in that fabric. Those clusters are managed by fabric controllers. Those are like the actual management instances in the Azure environment, carrying out tasks like deployment of applications, installations of new servers, and all the like. The utility fabric controller is like the fabric controller for fabric controllers, deploying other fabric controllers, which is also not very important here. Then if we look at the cluster, we see there is an additional level of network isolation, network forwarding implemented, and we have 20 racks that make up a cluster. Those 20 racks in turn consist of 50 compute nodes each, and there's a power distribution unit, also not too interesting at the moment. So, as we're focused on hypervisors, we have to look at the different nodes, and this is how such a compute node looks like. We have a standardized piece of hardware. Running on top of that is the Azure Hypervisor and several so-called partitions. Partitions is the Azure term for virtual machines. There is one root partition, also called root OS in the Azure environment, and several child partitions, all including some management functionality in order to deploy applications and the like in the Azure environment. We'll get a more detailed look on that later. So, if we look at this basic architecture, we also need to see that cloud is not the magical term that many people think it is. It's a bunch of hardware connected by some network elements, and there is some management functionality, some deployment functionality, and this is like the main part of cloud providers. They glue everything together with a lot of management scripts and ACL deployment rules and you name it. And it's all just hardware glued together. And at the very core, there is still the hypervisor. Without that, it would barely work. I mean, we would have more like classical hosting, but runtime breakouts are still a very relevant threat in cloud environments, and also a very interesting one. That's why we looked at it. Looking at hypervisors, I don't think you can give a talk on hypervisor without mentioning the difference between type 1 and 2 hypervisors. Somehow part of the picture is missing here, but I think you get the idea. Type 1 hypervisor is running directly on the hardware, and on top of this hypervisor there are several operating systems. A type 2 hypervisor is running on top of an operating system, virtualizing in turn several other operating systems. The interesting thing here is most people would think when they just install Hyper-V for the first time that it's a type 2 hypervisor, because you install just a plain Windows Server operating system first, then you add the Hyper-V row, which sounds like installing software in an operating system, but Hyper-V just gets installed directly on the hardware, virtualizing the original operating system as the so-called root partition. So just like the dynamic virtualization stuff with Blue Pill and all the like, that was also performed in the research area. Then, of course, we have different modes of virtualization. The oldest virtualization is full virtualization, aka binary translation, basically translating all the privileged instructions that cannot be executed directly by a guest system on the CPU anymore because it's virtualized, into a set of non-privileged instructions. This is necessary because if you would allow your guest system to run those privileged instructions on the CPU directly, you could not ensure that the hypervisor or other virtual machines don't get compromised from within a guest system. This is basically implemented in software and has thus some performance impact. The next step was to develop a hardware platform, Intel VTX, for example, also VTD, the Intel VT platform, to perform all those intercepting of privileged instructions in hardware, trapping on those instructions, and then handing control over to the virtual machine monitor. It's too bad. There are a lot of tokens in there. Too bad they already closed the token submission. And then we have something called para-virtualization, which is a concept that can be used in addition to both of those modes. There is no academic definition of para-virtualization. It basically just means that the guest system is aware of it running in a hypervisor and being able to communicate with that hypervisor in a certain way. There are different definitions on that, but that's like the most important part that we need to know about the hypervisor. No matter which type of virtualization a hypervisor uses, there are different parts of it that all can be attacked, and there is a lot of complexity to each of those parts. For example, the hypervisor is responsible for the device virtualization. Just as he has to do the memory management and the CPU scheduling, also the different devices have to be isolated, or the device needs to be virtualized and be made available to different guests that can then use it according to the resource allocation, and the usage of those interfaces should also be isolated against each other for the guests. Same holds true for memory management and isolation, which is a particularly difficult part. We will also have some slides on that later, explaining some parts of the memory management of the Hyper-V. This is one of the more low-level processor stuff that all the Intel guys know so much about when you hear those talks, like Galdeskin or also Rodrigo earlier, as well as CPU scheduling and isolation. Then all of the modern hypervisors also offer management interfaces. Those are often called hypercalls because this is the interface that provides a possibility for the guest system to communicate directly with the hypervisor, and if it's a privileged partition, also perform certain management functionality. We'll also describe that later in detail. And then there are additional APIs that might not really need it, at least not for management or for like core functionality, but that might offer additional functionality, like for example, you know, the copy and paste functionality between a guest system and the host system if you're using some virtualization on your desktop. These are like additional APIs that are offered by the hypervisor. Okay, having those different parts of the hypervisor in mind and the taxonomy of attack vectors in cloud environments, we will have a look at hypervisor breakouts and the history of those. One of the first hypervisor breakouts, I mean, except for the one FX mentioned in his keynote, but it's that old, I think only he can remember that, was VMFTP. I'm just referring to this like the modern world of virtualization. That was basically a flaw in the copy and paste and the shared folders functionality of VMware. That was a simple directory traversal vulnerability. So we were able to download arbitrary files from your hypervisor from within the guest. Then a more interesting breakout attack was 2009, presented at Black Hat by Kostya Koczynski, which was basically this thing everybody was waiting for. Execute some code in a virtual machine, and this results in code execution on the hypervisor. He was exploiting, this is an interesting fact, he was exploiting 3D API of the virtual graphic card, which allowed him to address or read and write arbitrary memory in the host system. So really nice thing, keep that in mind. Then in 2011, there was a KVM breakout. I'm not even going to pronounce that word, resulting from a dangling pointer vulnerability. Because apparently, the virtualized hardware, you can hot plug and hot unplug your south bridge while running. I don't think this is like an actual attack vector in a live operating system or a live computer, but apparently in a virtualized system, you can do that. So something closely related to device emulation. Then 2012 was a bad year for VMware we presented our VMDK has left the building attack. A more interesting vulnerability which could result in certain cloud environments in code execution on the hypervisor. And then 5 advisories in this VMware advisories referencing memory corruption vulnerability from the client system to the host system. Also 2012 was the Zen sysret vulnerability, a really interesting one, based on, I don't want to say a processor errata, but it was based on the way Intel and AMD handled the so-called sysret instruction, because Intel had a different way of performing this instruction internally. If you remember Rodrigo's talk, the internal translation to micro codes and so on, then AMD. And this different behavior allowed also a breakout attack from the guest system to the hypervisor. Then 2013, MS13092, this is the vulnerability we will discuss here, so I won't tell you anything about that. And then also very interestingly, 2014, 2 really bad vulnerabilities in VirtualBox. This one beginning of February, this one beginning of May. This one was just a very, very classical buffer overflow in the host-guest communication manager. This is basically a service that provides an interface to implement your own services for guest-to-host communication. And surprisingly, there was a buffer overflow in it. Nothing magical, just a plain buffer overflow, like in software. Then, as well, the VirtualBox Chromium breakout. Chromium is a library to carry out 3D graphics acceleration over network pointers. And interestingly, those network pointers were able to point to arbitrary location in memory. Does it somehow sound familiar? So it's like 5 years in between, and we still have the same problem in this software. We definitely should keep that in mind, especially when we are thinking about the virtual air gap. This virtual air gap might not provide as much isolation as the classical air gap between systems, and as Kostya Kaczynski put it nicely in his talk, VMware isn't an additional security layer, it's just another layer to find bugs in. It's not a VMware talk, however, I could not resist. This should just illustrate that a little bit. And we will go on with our talk. So, based on those vulnerabilities we saw, we also wanted to provide a short taxonomy on attack vectors as for hypervisors. And the first and biggest thing is the instruction set. If you have to fully emulate, or at least provide the full instruction set to a guest system without allowing the guest system to execute privileged execution, at least not while compromising the hypervisor, this is a really, really difficult task. When you think, when you communicate with an SSH server and you want to perform an unauthenticated remote exploit, there's a very, very tiny base of code that gets executed while you communicate with it. But now you have basically the full instruction set that you have to secure. So there is a huge attack base, and in this emulation there are most certainly a lot of bugs included. Then of course the management and additional channels. We had a lot of those in the examples, the VMFTP thing, also like our VMDK has left the building attack was somewhat related to management features. And then there is monitoring and caches. There was this talk, Virtually Impossible, by Galdiskin, and he said he won't go even into slight detail on caches because there will always be timing and side channel attacks on those, so we'll also skip those. Then we have memory management and devices as an attack vector. This is a really, really complex thing. If you look at all those extended page table algorithms that we had to look into a little bit for the Hyper-V research, and that we will provide some insight on. In the device emulation, this is really complicated stuff. If you ever look at the QAMO CVE history, you will see that it is really difficult to implement that in a safe way. All right, then we will have a look at the Hyper-V and see how those attack vectors transfer to Hyper-V and what that means for Hyper-V. Why did we focus on Hyper-V? Of course, there was very little research so far. There was one denial of service attack published in 2009. That was not based on any actual research, but on the reverse engineering of a patch from Microsoft. So very little research coverage. And we have the opinion that this should not be the case for any software as exposed as Hyper-V. Then it is used in a variety of corporate environments in the meantime, including Azure. If you read about Azure, you will read that there's the Azure Hypervisor and that Microsoft is not using Hyper-V. If you read a little bit more, you will see that the Azure Hypervisor is just the main line of development nowadays for Microsoft hypervisors, and that all like the features from Azure Hypervisor flow back into Hyper-V. So they are still closely related. And we have some screenshots here that are interesting to see. This is a screenshot from an Azure virtual instance. And as you can see, all the Hyper-V integration services are running. So there has to be some relation between Azure Hypervisor and Hyper-V. And then there is the CPU ID assembler instruction. And if you look at those, they are almost the same for the Azure Hypervisor and Hyper-V. We see that we have a different service branch here and a different service pack, but they are not that far away from each other. We will also see that when we look at our results. So if we want to perform a research project on Azure, it's also really interesting to look at Hyper-V, because bugs that you find in Hyper-V might transfer very well in Azure. Of course, you cannot test that, and we never did that, but they transfer really well. Let's just put it that way. Then we already mentioned that Microsoft Hyper-V is a type 1 hypervisor, even though it looks the other way. VMs are called partitions. There is the root partition, which is like the one privileged partition that performs all the management functionality on the hypervisor for like partition creation, configuration, and all this stuff. It uses hardware-assisted virtualization, Intel VT or the AMD variation of that. And there's support for enlightened and unenlightened systems, partitions. This describes basically the concept of para-virtualization, whether a partition or the OS running in a partition is aware of the hypervisor and it's communicating with it using hypercalls or the VM bus. This is the more detailed architecture of the Hyper-V. We have two interesting things that we want to focus on, and those are hypercalls, offering an interface from partitions, or at least enlightened partitions, directly to the hypervisor. So you can do like a regular API call, just as you would do a sys call, just not to the kernel, but directly to the hypervisor, and thus communicate with the hypervisor. And then we have the VM bus, offering an interface between virtual machines. For example, for high-speed communication, which is not supposed to go through the hypervisor. Of course, for performance reasons. So this is the Hyper-V architecture that we need for the remainder of the talk. And here we'll hand over to Felix to present you some of our more detailed results.
So, as Matthias already mentioned, when we started researching the Hyper-V hypervisor, we wanted first to try to map the attack surface, which is pretty important to understand which attacks might be possible. When we first started researching, we identified three interesting attack vectors. VM exits in general, hypercalls, which are a subset of VM exits, which are pretty interesting, as we'll describe later, and the VM bus itself, which is the message bus for the communication between the virtual machines. I will describe each of these three attack vectors in more detail now. So, as we mentioned before, Hyper-V uses hardware-assisted virtualization. This basically means that, so for the Intel version, this means that they are using the Intel VMX, so the virtual mesh extensions instruction set, which basically adds an additional privilege ring. So now you have not only ring 0, ring 1, and ring 3, or whatever. You additionally have a VMX root operation mode and a VMX non-root operation mode. So the hypervisor is running in VMX root operation mode, and the virtual machine in the non-root operation mode. And transitions between the hypervisor and the guest system are implemented using VM exits and VM entries. And of course, we are more interested in the VM exits. So how can the virtual machine transfer execution back to the hypervisor? So VM exits, first of all, they can be triggered on purpose, which is done when you're executing a hypercall. So Intel adds an instruction, which is the VM call instruction, which basically just jumps back into the hypervisor. And other than that, it can be a VM exit can happen when you execute a privileged instruction. So privileged instruction isn't actually the correct way So the correct or formal description of this, but basically the hypervisor can decide for a certain subset of instruction if they will trigger a VM exit or if they will be executed normally. So of course, if you try to access a system register or something like that, or if you even try to execute virtual machine management instructions inside the virtual machine itself, it will trigger a VM exit. And also stuff like, which is something Rodrigo mentioned before, the rd-rand instruction, which is this randomization function for hardware, can also be configured to trigger a VM exit, which is especially interesting if you think about hypervisors on a cloud environment, because basically if your cloud environment decides to backdoor your rd-rand instruction, you won't notice that, because VM exit are totally transparent to the VM guest. So basically this is the stuff the blue pill research was based on, that the operating system running inside the virtual machine environment can't decide or can't recognize that it's virtualized. And of course we have stuff like interrupts and API-C writes and stuff like that, which will also trigger a VM exit. So, as mentioned before, VM exits need to be transparent to the guest. So we want to be able to run guests which don't know they are virtualized. So if you execute a privileged instruction, it requires complete emulation of these instructions inside the hypervisor. And of course, if you have a little overview about Intel internals and the Intel architecture, this is not really trivial. So you have a lot of special cases and side effects and stuff you have to really implement correctly. But of course, if you want to support enlightened virtual machines, which means the virtual machine knows it's running inside a virtual machine monitor or inside a hypervisor, you have to provide some kind of feature so the operating system can detect it. A classical way, which is also the way Hyper-V implements it, is that they are adding additional function to the CPU ID instruction, which triggers a VM exit, and Hyper-V will return its version and additionally the guest permissions, which are quite interesting because they define which operations or which hypercalls the VM actually can perform inside the return values or inside the registers returned from the CPU ID instruction. And this is quite cool because now, in contrast to other virtual machines that might try to hide themselves from the user, if you are virtualized under Hyper-V, an unprivileged guest system user can actually query the exact version of Hyper-V he's running under, which might be pretty interesting if you try to exploit the stuff. So, because as you can see, you don't only see the major version, you even see the build number or the service pack. So this is the topic for VM exits. Now, hypercalls are more or less a special version of VM exit that are used for direct communication between the OS kernel, the virtualized kernel, and the hypervisor. They are something like system calls, but used for communication between the kernel and the hypervisor instead of the guest mode and the kernel. And the interesting thing about the hypercalls is that they are actually a documented interface. So Microsoft published the functional specification for the hypervisor, which actually describes every implemented hypercall in great detail. They describe the API and even include something like C header files, so you can actually use this hypercall API. And it's designed to be used by third parties. So you can, for example, extend your antivirus solution to support some kind of insight into virtualized systems and stuff like that. And of course, there are known security boundaries. So if you have any idea about implementing a hypervisor, you know the hypercalls are going to be attacked by a potential attacker because they are one of the main interfaces. For Hyper-V in practice, they are used by enlightened partitions to improve performance. So basically, you don't have to wait for a VM exit to trigger by itself. So for example, the virtual machine can simply trigger a hyper call on demand. And especially interesting is that for Hyper-V, the hypercall interface is also used by the root partition for management of the other partitions. So actually the creation, as you can see in this example, the creation of an additional partition, so of an additional virtual machine, is completely implemented in a single hypercall. And even stuff like read registers from a different virtual processor or set register values of a different virtual processor can be reached using hypercalls. There's actually only a single check inside each of these hypercall handlers to ensure that this stuff isn't called from a normal partition, but only from the root partition. So we won't go into that in too much detail, but one thing we find interesting is if you have a memory corruption inside the hypervisor, so you can write arbitrary memory, there's basically 1 byte you can just overwrite or write a null to it, and then your virtual guest machine can use this hypercall RP to arbitrarily get and set registers of different partitions, which is actually quite cool, because that might make a hard to exploit memory corruption inside the hypercall to the perfect exploit, because after that you have a stable API to use. So hypercalls were the second attack surface. The VM bus is the third one. And the VM bus is actually the most interesting one, at least in my opinion. Basically, the VM bus is a message bus used for communication between partitions. In the default configuration, only the root partition can communicate with each guest partition, so the guest partitions can't communicate between each other, because that would open something like side channel attacks, and you could bypass the hypervisor. And they are actually implemented using memory pages that are mapped inside multiple partitions at the same time. This is, of course, used for performance-critical tasks. If you imagine you want a virtualized network interface that performs quite fast, you don't want to send every network packet using the hypervisor, because then you have to match context switches. So instead, you just map the memory in the root partition and in one of the guest partitions, and then you push the packets inside this memory space. The interesting thing is that this opens a large attack surface, because basically if you write data into this memory region from the guest partition, it's going to be passed inside the root partition. So this potentially doesn't compromise the hypervisor itself, but if you have a root shell or admin access or code execution on the root partition, the hypervisor isn't that interesting anymore. So this is a large attack surface. But when we actually considered a research path for this Azure environment, VM bus is a cool target, but it's not the most practical one. Because basically we are working with Hyper-V and try to use our research results for the Azure cloud. And the possibility that there's a large implementation difference between Azure and normal Windows Server implementations on the VM bus implementation. So we are not sure what kind of services are running in the root partition in the Azure environment. So this makes potential vulnerabilities we find in Hyper-V. It's quite possible that are simply not usable for Azure. So the VM exit handling, which I described before, might be really interesting, especially considering some special cases and error conditions. But to be honest, we are not that good at processor internal stuff. So we are not Gal Diskin. So this seemed to be pretty hard research for us. At least we didn't try it at first. So what's left are the hypercalls. Hypercalls are basically, as I said before, a documented API. They are isolated functions. So for each hypercall, you have a hypercall handler. It's relatively trivial to identify this hypercall handler inside the binary. And basically, then you are working with a normal C function. So even if you are not really the virtualization guru or low-level expert, just working with a single hypercall handler and auditing this handler for security vulnerabilities is possible. So we decided to start looking at the hypercalls and hoped to find some low-hanging fruits. So as the first, so that we could gather some results. Of course, we had some expectations when we started this research. So the hypervisor itself has a pretty minimal feature set. Microsoft is actually quite proud. They outsourced a lot of implementation details to the root partition, so they could keep the hypervisor pretty small. It's actually a relatively small code base, so it's like a 2 megabyte executable, which if you ever reverse engineer a 2 megabyte executable is still pretty large to just analyze the assembly code, but it's more or less like 60 lines of C and assembly code. So that's at least an official statistic we found on the internet. And if you compare that to like 50 million lines of code, you probably have, when you're looking at the Windows Server kernel, it's a pretty small code base. And in addition, as Matthias already mentioned, until we started our research, there was only one serious public vulnerability in Hyper-V incomplete, and this affected the VM bus, which we would not be looking at in too much detail. So we concentrated on the Hypercalls, which until then looked pretty stable or pretty safe. And in addition, you have stuff like this. So Microsoft actually performs research to perform formal verification of the hypervisor. So academic research to prove that there are no memory corruption vulnerabilities or stuff like this inside the Microsoft hypervisor. And of course, you have something like the Microsoft Security Development Lifecycle. And Microsoft is one of the few vendors who actually have the balls to go to Black Hat and publish their security architecture of their product and are saying like, yeah, our product is secure, so here's the presentation. So we had pretty low expectations to find any serious vulnerabilities. Yeah, I just noticed I'm a bit too fast, so I have to slow down a bit. So
no problem. Can bring back time. I'm happy about this.
So the fortunate fact then was that just 2 days later, most of the 2 days were actually spent up setting the lab and installing Hyper-V. So it was more like 1 day and a half. And then we got the first blue screen. So this is a hypervisor blue screen. So we actually find a denial of service inside the hypervisor from a virtual machine, from an unprivileged virtual machine. You can see the picture quality is really bad because we performed this denial of service actually on physical hardware. So I had to grab my smartphone and send Matthias the picture so he could see that we crashed it successfully. Of course, crashing is always easy. So what was the really difficult part was actually understanding the bug. So the root cause analysis started after these 2 days. And so we basically had to dig up the binary and look at the open up IDA and start looking. So Hyper-V is mainly implemented in 2 executables, depending if it's for Intel or for AMD. So we concentrated on the Intel executable. If you ever worked with Microsoft binaries, you are used to getting public debug symbols, so at least you can get the function names. Unfortunately, they aren't available for the hypervisor itself. However, some of the symbols or some of the functionality included in the hypervisor executable is actually identical to the functions used in the winload.exe or the hvload.exe. Mainly stuff like networking code, USB stack, or the basic debugger implementation, so the support for the WinDBG debugger. We were actually, so it wasn't our idea, so full credit for this idea go to Gerhard, which is an author from securitylab.ru, which published some of his research on Hyper-V, so we've stolen this idea from him. And after that, we at least had some basic public debugging symbols which we could work with. So debugging a hypervisor is sometimes quite hard. In the case of Hyper-V, it has a WinDBG interface. So you can use the normal Windows debugger to connect and to debug Hyper-V. So for normal hardware, if you really work with physical hardware, which we started, you can use the serial port, fire via Ethernet, whatever. Unfortunately, this is either slow or doesn't work reliably. So we had some kind of problems getting this setup really usable. Fortunately, we noticed we don't need dedicated hardware anymore because current version of VMware Workstation and Fusion, for example, actually support nested virtualization. So they use their binary translation mechanism to actually emulate the Intel VT instruction set. So we can you can install Hyper-V inside VMware Workstation.
That was also a little bit confusing for the people in our exploiting hypervisors workshop because they really had a hard time understanding, okay, which system is running where now and what am I exploiting at the moment, because it's very nested.
So we got a relatively easy setup inside our virtual machine, but one of the ugly things about debugging Hyper-V is that there's an extension DLL for WinDBG, which is required to really have Hyper-V specific debugging functionality. This is the Hyper-V extensions DLL, I guess. And this isn't publicly available. So if any of you guys have a copy of these, I would be happy to talk to you later. Because this implements a lot of features you could really use if you try to debug Hyper-V or if you try to analyze the architecture. So after we got the initial setup, we started looking at the bug. What's the reason for the bug were? And as we said before, it was in the hypercall interface. And basically, if you look at the lowest level of the hypercall interface, it works by executing a VM call instruction. And all the arguments, so all the hypercall arguments, at least they have different calling mechanisms. So like you have on a normal user space environment too, but they have something like slow calls and fast calls. And for slow calls, the hypercall number is in the RCX register, and the guest physical address of the input and output data are in RDX and R8. So if we are talking about Hyper, we always have three kinds of different addresses. So we have the guest virtual addresses, the guest physical addresses, which then get translated into the system physical addresses. So for the hypercalls, we have to work with the guest physical addresses, which interestingly isn't really documented, in which was basically the root cause why we found this bug, because we tried to use virtual addresses at first. So when you actually perform this hypercall, you have so before reaching the call handlers for this specific hypercall, they perform a couple of checks. So something like the hypercall number has to be valid, the alignment of the addresses you enter should be right, and they check that the hypercall actually comes from ring 0. So that should be a normal check every hypervisor implements, but actually I think Xen had a bug last year or something where they didn't check that. So where you actually could execute hypercalls from user space. So in this case, our exploit requires that you are inside the kernel of the virtual machine. So you have to have root permissions or something like that. And after they perform these checks, they actually check the upper boundary or they check for an upper boundary concerning the input guest physical address. So in this assembly snippet, you can see that the RSE register contains the input guest physical address, so the guest physical address that's pointing to the actual hypercall input, and it's compared to some kind of upper limit. And if this limit, so if the input GPA is just too high, an error condition is raised. And this error condition will eventually result in the execution of the EPT error handler, which is the extended page table error handler. So extended page tables are basically a mechanism introduced by Intel to improve the performance of hardware-assisted virtualization. So you don't have to keep something like shadow page tables in software anymore, but instead you have an extended page table which performs the translation between the guest physical addresses and the system physical addresses. So this error routine is actually triggered whenever a virtualized system accesses an invalid guest physical address, which shouldn't happen that often, but of course it can happen. Now, the difference is it checks if it's a read or write error. In our case, it's a read error because it's only the input data. And then the function I named EPT read error is triggered. And now the input address is used as an index into the extended page table for this virtual machine or for this virtual CPU. And of course, we control the RRX register, which is used as an index. and there isn't a really check for the upper limit, so we trigger this error condition by inserting a really large value inside the input address. There isn't a check for an upper limit, so basically we have a classic out-of-bound error access. The trigger which we used for the denial of service vulnerability is basically the classical for one, for one, for one.
There are even people who have a Twitter handle.
Yeah. Yeah, of course, our vulnerability trigger was inspired by FX, so full credits for this vulnerability go to him, I guess. Yeah, so we reported this bug, and so if you can see, it's basically, first of all, only a read violation, so we don't have a direct way to trigger a memory write. And we started looking into it, but then business got in the way, and we reported it to Microsoft. And we considered it at that time a denial of service. So we could access invalid memory, but we didn't get quite a privilege escalation or something else going on. Interestingly, the Microsoft guys actually considered it a potential privilege escalation. Now, if you actually read Microsoft advisories, you know that in the last years they started to consider every vulnerability potentially exploitable. So that hasn't tell you too much. But the interesting thing is that Azure was actually affected. So this vulnerability could have been used to crash an Azure hypervisor. And Matthias gave a quick introduction into the Azure architecture. And one thing that's especially cool when you consider a denial of service vulnerability in this environment is that when you have a virtual machine and its hypervisor crashes, the virtual machine automatically restarts on a different hypervisor. So now imagine you have this vulnerability and put the exploit code basically in auto start, and then you just walk away and wait until everything goes boom. So yeah, we didn't do that, but we could have. Yeah, of course, the interesting thing is the potential privilege escalation. So as said before, we got bugged the last few months to present a potential breakout out of this vulnerability. Unfortunately, the bug cannot be used to get a memory write corruption, so we can't simply write somewhere in memory. However, we were working with the extended page table, and we can actually exploit some kind of logic vulnerabilities because we can supply an arbitrary page table to this function, so we can control which memory location is read and which value will be there. And we have some kind of raw ideas how to exploit that, but basically before I start rambling about potential exploitation vectors, so we don't have a privilege escalation exploit demonstratable yet, so we hope we can present that in a couple of weeks, months, or whatever. So now comes the live demo for the denial of service vulnerability. I saw Enno's tweet that you have to clap when a shell pops up. Now in this case you have to clap when the blue screen pops up. So. So you can see this is a really cool setup. I have to go into a bit of detail in this. So this is basically a Microsoft Server 2012, which is the root partition running inside the VMware Fusion on my Mac. And inside of this root partition, so virtualized now, is running an, if I find my mouse, is an X Ubuntu system which we use to exploit this vulnerability. Because basically you have to come from kernel space. And it's easier to write Linux kernel modules than Windows kernel modules. So basically we decided on Linux.
There is a shell, but that's not the point.
Yeah. But you can't. So the actual exploit code is basically implemented in a kernel module we named Hyper. Yeah, and it's triggered not directly, but instead we write a short command line tool, which then triggers the denial of service. And yeah, that's the blue screen. So. Yeah. So now I think I hand back to Matthias for the conclusions.
Yes, the first conclusion that we have is that hypervisor security and research is not hard. As you could see, you just have to implement something to be able to do hypercalls, and you can start messing around with really internal functionality of the hypervisor. This is something even I can do. I'm not a savvy exploit writer or anything like that, but even I can implement some kernel module that triggers denial of service vulnerability in Xen or Hyper-V. However, for the attempts to code execution, I have to hand over to Felix because how did you put it? Once you start wearing suit checkers, there's just not enough time for that. But this is basic stuff even I can do. So you should definitely look into that. Then the other conclusion is that hypervisor security research is really hard once you dig deeper into this real deep memory management and scheduling and context switching stuff. You really need to spend a lot of time in there, and you really wish you would have debug symbols. This can get really difficult once you look for a few hours on that. And even verified code contains bugs which can easily be exploited, which goes very well with the next conclusion that there is still a lot of fun to be explored. And virtualization gains a lot of features. Every new hypervisor version has additional features, but the security is not continuously improved. During our exploiting hypervisor workshops, we've accidentally found an additional denial of service bug in VMware. So there's really plenty of stuff to be explored yet. And one important message of our talk is that more researchers should do that. The VirtualBox bugs that were discovered this year is also more like traditional software vulnerabilities. But we think that a lot of researchers don't look into hypervisors because they think it's too complicated, but you should definitely start doing that in order to make the theoretical practical and provide at least some denial of service exploit code. Thanks for your time.
Okay, Felix, Matthias, thank you very much. Questions, please.
Take this timing here.
Basically, I have two questions. First, is it right that this vulnerability has been fixed in the meantime?
Yes,
yeah.
Otherwise...
So you were demoing on an older version, unpatched version of the hypervisor?
Yeah.
Yes.
Right.
It was patched in MS 1392 and also in Azure.
And then the real question is, so are you telling us that no one has ever tried fuzzing the input parameters of a hypervisor?
So that's actually quite interesting because I have a theory why nobody finds this bug. So actually Microsoft provides an API you can use to do hypercalls, and then you fuzz the actual value you pass to the hypercall. But you never fuzz the actual guest physical address. So if the researchers, so Hyper-V researchers are probably Microsoft based, so they're probably working on with using Windows. And then you just use the API. And we tried to do it on Linux, and then we got the layer deeper, and then the bug popped up. So at least it's my theory.
The contents of the hypercall handlers are probably rather well tested, but the way how they are called, this execution path is probably not that well tested.
Okay, more questions, please.
So you said you can mess with kernel easily with hypercall, right?
Yes.
So what do you think as a protection? What if your system has a microkernel underground? I mean, hypervisor definitely, but which is not virtualized with microkernel.
Well, if they offer the hypercall functionality, there will still be a certain kind of interface that you can attack.
It's not the same. It's not the same exactly what we have with Microsoft. I mean, or VMware, because there are very few hypervisor based on microkernel, right?
That's true. The attack surface reduces, of course, and we haven't tried that yet.
Okay, more questions?
Thanks again.
Great.
Hello? Up here.
So, just a short question. the new Gen 2 VMs do more functionality over the VM bus. Are you looking forward for that?
Yeah, so basically the VM bus is something we want to spend dedicated research time on, because basically the hypercalls are something you could probably secure pretty good, but actually securing the VM bus, and especially if the new VM generation relies even more on the VM bus. So the more functionality you put inside the VM bus, the more attack surface you get. And for the VM bus, it's pretty hard to actually, so you have to build your own toolchain to attack the VM bus, so therefore we are pretty sure there isn't that much research performed on that yet. So we plan to do that. Maybe next year on Troopers.
Okay, so if there are no additional questions, now it's time for clapping. Thank you very much.
Thanks.
Danke, and sorry.
Kein Problem.
We'll have some like 5 to 10 minute break.